One of the problems I think I intended to do, I didn't even really look at what the problems were. I think I remember signing it, but it doesn't matter. One of the equations is like dq dt equals R1C1. Yeah, I did give you this one. R1C1 plus R2, and I might have had just plain R's on it, I don't remember, Q over V. And it would be minus R2 Q over V.
That's exactly what
There's a simple interpretation of this equation, but let's just first look at how you're going to solve it. While you're looking at that, I'll just benefit here. These are just interpretations of HTML, because sometimes I forget to run my HTML through the code interpreter. It just does, that's a subscript, looks like this. This is a superscript. The superscript is between this and this. And asterisk in front of a Greek letter means that Greek letter. Okay. So anyhow, how do we solve this equation?
Would it help to bring the Q over?
I'm sorry?
Would it help to bring the Q over?
Okay, so if you bring this over here, it becomes a first order linear non-homogeneous equation, right? So it could be okay, or also separable. Okay. So if we treat it as a separable equation, we're going to write this as dq over R1C1 minus R2, and I'll write it as R2 over V times Q. So it's just a constant times Q, and it doesn't look as much like you got a denominator. You just treat that R2 over V. And that equals R1C1 dt. Okay? So we've got to integrate this. Now how are we going to integrate this? What's the form of the integral? If we, no, I'm going to go ahead and put the integral sign in front of these. You're going to have to do substitution. What's the obvious substitution? Well, it might not look exactly like what you might be thinking of, but you just let U equal R1 C1 minus R2 over V cubed. So that kind of an unnecessary step here, but I'll do it. Derivatives, negative R2 over V, simple constant, which means you're in pretty good shape. So the du is negative R2 over V dt, dq. So that dq equals negative V over R2 du. So now we've got a dq, but we've got a multiple of du over u. So we have the integral of negative V over R2 du over U. And the BQ is this. That's your U. Okay? That's going to be a simple natural log. And that equals the antiderivative of this, and, general antiderivative. So it's R1C1, and I don't want to use C for a constant because I'm using C's for something that has meaning for the interpretation of this equation. Okay? So we have this, and then this just, this is just a constant, so we get negative V over R2 times the natural log of the absolute value of U, and it's R1C1T equals R1C1T plus integration constant. Okay? Etc. And if you don't remember how to deal with this, look back at the videos from last time, I think, or the time before. Okay? So you're going to multiply by negative R2 over V. So over here, you're going to get R1, R2, C1 over V times T is negative. But of course, a natural log of absolute value of U would be equal to that, so that U equals plus or minus e to the k, e to the negative R1, R2, C1 over V times T. So that U equals A e to the negative R1, R2, C1 over V T. That's all exponent there. Okay? And of course U then is R1, C1 minus R2 over VQ, right? So that and you can solve for Q. That's very straightforward. Okay? So the steps are really standard. Practice a few. It becomes fairly natural to see where you're going and what you need to do. Okay? Not a particularly difficult substitution. It's a little messy with all the symbols. I'm not even sure I got them all in the right place, but I don't see any reason to think I didn't, except that sometimes I don't. Okay? Then you can go back and check things like, okay, if I well, I'm not, yeah, okay. Okay, so what's this mean? Well, here's kind of what it means. You have a tank here, and you got a solution flowing in here. And then you are pumping solution out. Okay? So concentration C1 goes in at rate R1. Okay? And mixed solution goes out at rate R2. Q is the quantity of solute in the tank. And I'll give you a more specific example, just so you know what solvent and solute mean and stuff. Simple concept. The quantity of solute in the tank, and V is the volume of mixed solution in the tank. We assume instant mixing, which isn't really necessarily what happens. Okay? If the tank is a lake, and what's going into the lake is a certain concentration of chemicals or sewage or whatever, it doesn't mix instantly. It does flow out eventually. Okay? The mixer does flow out. So, it's only an approximation to a real situation. You have to worry about the diffusion of the stuff through the lake and currents and the shape of the lake and the shape of the lake bed and everything else. Okay? And that'd be really, really complicated. So, but the principles we use here, if you just know how to solve the diffusion equation and figure out all the currents, you'll never get it right with a real world situation, but you still get insight as to how things work. Okay, from this sort of thing. Of course, if you're a chemical engineer, you're always mixing things in tanks. Okay. You still have to worry about the latency, the delay between the stuff going in and being thoroughly mixed. But if you've got, good mixers, it's pretty close to instantaneous. But for some reactions, you really have to analyze it more deeply than that. So it's an oversimplified situation. It still works pretty well for a lot of things. And illustrates differential equations in a way that I would think is pretty straightforward. So, I want to move that board over, and I got this thing in the way, so I'm going to move it. Okay. So, example. %, salt solution in water flows in at 5 gallons per minute. Okay? Tank capacity, 100 gallons. Outflow at the same rate, 5 gallons per minute. Okay? The outflow rate doesn't have to equal the inflow rate. Okay? At least until the tank is full. And if the tank is full, 2 rates. To keep it, if you're going to keep it full, it has to. But of course, this could go out faster than this, so the tank could be full, so it could be gradually emptying while the thing is mixed. Okay, or it could initially be empty, which wouldn't be any fun at all, because you always just have this, okay? Or it could have just plain, assume the salt's in water yet. Maybe the tank is a third full of water, and this 10% solution's flowing in. So what's going to happen is solution's going to flow in until the tank's full, so the outflow rate doesn't have to equal the inflow rate, and the outflow rate might be variable. Okay? So it can get kind of complicated. That makes sense? Okay, but this is simple as possible scenario. Now, there's more to it. I said the tank capacity is 100 gallons. I didn't say if there's any water in it. If there isn't, then it's not all that interesting a problem. So we'll just say simplest case is the tank I could just say it's originally full of water, but I'm going to say it's originally full of 2% solution. Okay? Well, can you identify R1, C1, V, R2? Okay? Very simple, it's just, you know. So it's going to be dq dt equals what? 5 gallons per minute times 10%. Now, what we're modeling is Q. Well, I said Q is the quantity of solute in the tank. Okay? So, if 10% solution is flowing in at 5 gallons per minute, then now we're going to kind of oversimplify it and say we measure the salt in gallons. You know, what exactly does that mean? Gallons of dry salt? No, it's wet. You know, it's already dissolved. So we're taking a little liberty with the physical reality, but the principle's okay. We can adapt that, but we don't want to deal with those questions. We're just going to say it's gallons per minute. Okay? Or if you wanted, it could be an alcohol solution, but they clearly miss it when the volumes don't add. And, you know, it's still a little bit weird. Okay? So, we're going to say that, okay, what you got there is then pretty clearly half a gallon of salt per minute coming in, right? 10% of 5 gallons is half a gallon. So that's your R1C1. Okay? Not sure the camera's picking up everything over here, but there it is. Okay? Outflows 5 gallons per minute. So I guess my question is, if we know Q, at what rate is the salt flowing out? Now Q's changing. You got 10% solution going into a 2% solution. The concentration is going to be increasing. The mixed stuff is going out. So Q's variable, so we can't say what Q is. Q can be anything. Well, it's probably not going to be any less than 2%. It's not going to be more than 10%, but you don't know what it is. Okay? Because the greater the concentration in the tank, the less change there's going to be. As the concentration approaches 10%, you know, the change approaches zero, the change in how much stuff there is in there, because you got 10% in and you've got almost 10% going out at the same flow rate. Okay? So how do you calculate? If I tell you what Q is, okay, well let's just, you know, let's do a numerical example just to grasp this, because this is hard for people to do for some reason. Very simple situation, but it's hard for people to grasp. And I don't know you can necessarily track that completely to deficiencies in our educational system, although I think In fact, the word problems are hard, so you don't do many of them. Okay? If you got a class full of people that don't want to do them, you cater to that. But I'm not sure that's what's really going on. Okay, so, originally you've got 2 gallons of salt in the container, right? And you're not going to have more than 10 gallons because it's obvious that concentration will never exceed what's going in since you started with a lower concentration, right? Okay? So let's just say right now there's a 6% solution in the tank with 10% flowing in. Okay? And 5 gallons per minute flowing out. So at what rate is salt flowing out? So it comes down to this. If at some instant the concentration is 6%, then at what rate are you losing salt? At what rate is salt flowing out? So, for example, at some instant, okay, well, 6% solution, what rate does salt flow out? Can you tell me?
Wait, it's the, so we've got 6%, that's 6 gallons out of the 100 is salt.
Yeah.
And multiply that times 5 gallons per minute is, or divide that by 100 gallons, you get 0.06 times 5.
Yeah.
And 1.5 times 5 is, or 0.1 times 5.
Well, you don't have to worry about the arithmetic. You should do it in your head,
Yeah.
then check it with a calculator if you need to, okay? But 6% of 5 is 0.3, right? And you can kind of relate that to make sure you've got the right decimals and everything. 10% of 5 is 0.5, right? 6% is a little less, but not that much less. And if you are used to thinking about numbers rather than punching them in, then it becomes pretty quick and obvious if you've got, reasonable skill for mental arithmetic, there's going to be 0.3. Okay? So you kind of check things out that way. Saves a lot of time, and it's that with a backup of a calculator or computer algebra program is pretty reliable. If you're not doing both, I get worried about you. I get worried about whatever you're trying to engineer, okay? But there are other ways to check too. There are other ways to check consistency. Have 2 different members of a team do the same stuff. But that's kind of a waste of manpower if you got reliable people. Depends on how critical it is not to have that thing blow up and kill everybody. Okay? Okay, so anyhow, well, 6% of 5 gallons per minute is 0.3 gallons per minute. Okay? So, and incidentally then at this instant, Q's changing at a rate of 0.5 gallons per minute minus 0.3 gallons per minute. Now, why is that? Well, you got salt flowing in, you got salt flowing out. At what rate is salt flowing in?
It's flowing in at the rate of 10%.
Well, 10% of what? 5 gallons per minute. It's inflow of salt minus outflow of salt. Okay? So after another minute, how much salt do you think you're going to have? I mean, it's got 6% solution, it's got 6 gallons of salt, right? If it keeps changing at this rate, in another minute, it's going to have 6.2 gallons. But it won't quite have 6.2 gallons because the outflow rate is going to be increasing as the concentration increases. So,
So it's just like when we were back in the first portion
yeah,
of the class.
exactly, you're projecting the
Yeah.
slope
Yeah.
forward. So you can do the same thing with this, but you don't need to because it's easy to solve this equation. It's a simple separable equation. Okay? That makes sense? Okay? So, one reason we started with the whole picture in the plane, well, 2 reasons. One, to at least make it plausible that these things have solutions under appropriate conditions, and also because it's an important method, because if you can't solve the equation exactly, you can with this one, but if you have an equation you can't solve exactly, let's just say that you got a pipe in the bottom, and as the water rises, the outflow rate increases because you got more pressure. Okay? Now that equation, I don't know if you can solve. I'd have to write it down and look at it. Okay? I suspect maybe you could, because it's just going to be a first order linear with a non-homogeneous part. I think it's still linear. Maybe it's not. I'm not thinking all that far ahead right now. Okay? But it would be easy to write that equation down, and we probably will before long, just so you can see. Okay, maybe we'll even do it here in a little while. Okay, but anyhow, you got 0.2 gallons per minute at this point. But you know that the rate of outflow, or the rate of change of Q is going to keep decreasing. Because as the concentration increases, this thing you're subtracting here is going to increase. And this is going to stay the same. Okay? So that's, you want to have a handle on those details, rather than just, here's the equation, solve it, plug these numbers in, and there's your solution. What? Is there any intuition involved with this? Well, yeah. I think it's important for engineers and scientists and people who use mathematics to have some intuition. Okay? Okay, so, well, now my question then is, if we know Q, then how do we figure out at what rate salt's flowing out? Now, here we didn't know Q, but I could have said, instead of the 6% solution, I could say, if there's 6 gallons of salt in the tank, right? So whatever Q is, you're going to be able to figure out the percent solution, right? What's that going to be? Like if Q is 8 gallons, what's the percent solution? 8. hundredths, 8%, because you got 100 gallons in the tank. Well, in general, if you have a different volume of tank, what are you going to do? You're going to divide the amount of salt by the volume of the tank, or at least the volume of solution in the tank. In this case, the tank will always be full. Okay, so the percent solution is Q over V times 100%, because this is a decimal, but you want, if you want 6%, you better take the 0.06 you get when you divide Q by V and multiply by 100%, right? Okay? Then the outflow rate is this percent of 5 gallons. Okay? And of course, to change the percent to a decimal, you just don't do that, so you just have Q over V, right? Well, that's Q over V times R2. R2 is the outflow rate, okay? Which is the same as the inflow rate in this case. It's just this. Okay? So, again, dq dt equals C1 R1. That's your 10% of 5 gallons per minute, right? Minus Q over V